For nearly 3 minutes, this train continued racing across Germany while a broken steel wheel slowly destroyed the tracks beneath it. Nobody on board understood that disaster had already begun. If you enjoy stories like this, don't forget to like the video and subscribe to the channel. In the late 1990s, Germany was proud of one machine above almost everything else on its rail network: the Intercity Express. Known simply as ICE, it represented speed, precision, and modern engineering. For millions of passengers, these silver trains became a symbol of reliability. They connected major cities at incredible speeds, while offering quiet cabins, smooth rides, and a level of comfort few rail systems could match at the time. Among these trains was the ICE-1, the first generation of Germany's high-speed rail system. Introduced in 1991, it quickly became one of the most recognizable trains in Europe. Long white carriages, a sleek aerodynamic shape, and speeds that felt almost futuristic for everyday travel. By the late 1990s, the ICE network had already transformed rail transportation across Germany. Passengers trusted these trains completely. Business travelers used them every day. Families boarded them for vacations. Tourists saw them as part of the modern German experience. The trains were designed to move quickly, quietly, and efficiently between major cities. Most people stepping aboard never imagined that one small hidden defect could eventually trigger one of the worst railway disasters in modern European history. On the morning of June 3, 1998, ICE Train 51 left Munich and headed north toward Hamburg. The high-speed train consisted of 2 power cars and 12 passenger coaches. Nearly 300 people were on board, including passengers and crew members. Inside the cabins, the atmosphere felt calm and routine. Travelers settled into their seats as the train moved smoothly across Germany under clear summer skies. As the train accelerated across northern Germany, passengers relaxed into their seats. Some read newspapers, others worked on laptops or quietly talked with friends. Food carts moved through the aisles. The train itself felt stable and smooth. At speeds approaching 200 kilometers per hour, the ICE-1 was performing exactly as it had been designed to perform. Far beneath the passenger cabin, an unseen mechanical problem was slowly getting worse. One of the train wheels had developed a small crack inside its outer steel ring known as a wheel band. These components were built to handle years of pressure, vibration, and high-speed travel. But over time, constant stress weakened the metal. With every kilometer, the damaged section became more unstable while the train continued moving north at full speed. The damage remained invisible to everyone on board. No passenger could see it. No crew member could hear it. And yet, with every kilometer, the crack expanded further. The train continued racing north at full speed, while a critical component beneath the first passenger coach moved closer and closer to complete failure. At approximately 10:56 in the morning, the wheel band finally broke apart. A large section separated from the wheel at extremely high speed. The metal fragment slammed upward through the floor of the first passenger coach. Inside the cabin, travelers suddenly heard a violent impact beneath their feet. Several passengers immediately noticed that something was wrong. A piece of metal had torn through the floor and become lodged inside the cabin between passenger seats. People looked around in confusion. Some believed the train had struck debris on the tracks. Others feared there had been a mechanical failure. But at first, nobody understood how serious the situation truly was. One passenger decided to search for a conductor and report the damage. It was a reasonable decision. The train was still moving smoothly and there was no immediate sign of derailment. The conductor, however, was located several cars away from the damaged coach. While the passenger moved through the train searching for assistance, the ICE continued traveling at full speed. During those moments, the damaged wheel band continued striking the railway infrastructure below the train. With every second, the loose metal component hit sleepers, rails, and track equipment. The train covered kilometers in less than a few minutes. Inside the cabins, most passengers remained unaware that a catastrophic chain of events had already begun. Exactly 3 minutes after the wheel band failed, the train approached a complex section of railway track near the town of Eschede in Lower Saxony. Ahead were several railway switches where tracks crossed and connected with one another. Under normal conditions, trains pass through the area safely every day without incident. As the first damaged coach moved across the track switches, the broken wheel assembly suddenly lost proper alignment with the rails. One set of wheels briefly left the track. However, the train did not immediately separate, and the braking system was not triggered. To passengers inside the cabins, the train still appeared to be moving forward normally. Moments later, the damaged wheel struck part of another railway switch. The impact forced the mechanism into a different position while the train was still moving through it at nearly 200 kilometers per hour. This changed the direction of part of the train in an instant. The first coaches continued one way while following coaches began moving another. The forces involved were enormous. One carriage was violently pulled apart as different sections attempted to follow separate tracks. Within seconds, several coaches lost stability completely. Cars behind them began leaving the rails at high speed. What had started as a hidden crack inside a wheel assembly was now becoming a full-scale disaster. One derailed carriage slid sideways across the railway line and struck the support columns of a highway bridge positioned above the tracks. The impact severely weakened the structure. Almost immediately afterward, the bridge began collapsing directly onto the moving train below. Some coaches managed to pass beneath the bridge moments before it fell. Others were struck as the concrete structure collapsed onto the train. Passenger cars behind the impact zone collided with one another in rapid succession. Several coaches overturned or compressed together as the train finally began breaking apart. The emergency braking system activated only after major sections of the train had already separated. By that point, the destruction stretched across a large area of track. Dust filled the air. Metal and debris covered the railway corridor. Survivors inside the damaged coaches struggled to understand what had just happened. Nearby residents heard a thunderous sound echo across the area. Some initially believed an explosion had occurred. Others saw dust clouds rising above the tracks and rushed toward the scene. Emergency calls quickly flooded local dispatch centers as witnesses described a major railway accident involving a high-speed train. Emergency crews from nearby towns arrived within minutes of the disaster. Firefighters, police units, medical teams, and railway specialists rushed toward the crash site near Eschede. What they found was a scene of massive destruction spread across the tracks beneath the fallen bridge. Several passenger coaches had suffered severe structural damage, making rescue operations extremely difficult during the first critical hours after the accident. Emergency responders carefully searched through twisted metal and unstable structures while trying to reach trapped passengers. Communication was difficult in some areas because parts of the train were compressed tightly together. Despite the danger, rescuers continued working for hours in an effort to reach as many survivors as possible. Passengers who escaped with minor injuries helped others leave damaged coaches. Some guided confused travelers away from the tracks. Others comforted injured passengers while waiting for medical teams to arrive. The disaster scene quickly turned into a massive, coordinated rescue operation involving hundreds of personnel. In total, 99 passengers and 2 railway workers lost their lives in the disaster. Dozens more suffered injuries of varying severity. It became the deadliest high-speed rail accident in German history and one of the most significant railway disasters involving modern high-speed trains anywhere in the world. As investigators examined the wreckage, attention quickly focused on the failed wheel band. Experts discovered that fatigue cracks had formed over time due to repeated mechanical stress. Under high-speed conditions, the damaged component eventually broke apart completely, triggering the catastrophic sequence that followed. Investigators also studied the design of the wheel system itself. Earlier train models had used different wheel constructions, but the ICE-1 relied on wheel bands intended to reduce vibration and improve ride comfort. Unfortunately, the design introduced vulnerabilities that became critical when hidden cracks developed. The investigation revealed how several small factors combined into a catastrophic outcome. The wheel failure alone did not immediately destroy the train. Instead, the disaster unfolded through a sequence of events involving track switches, delayed detection, and the enormous forces created by high-speed movement. One of the most disturbing conclusions involved timing. Only a few minutes separated the initial wheel failure from the derailment. Passengers and crew had almost no opportunity to fully understand the danger before the train entered the switch area. At 200 kilometers per hour, even brief delays became critically important. Railway experts across Europe closely followed the investigation. High-speed rail networks were expanding rapidly during the 1990s, and many countries viewed Germany's ICE system as one of the safest and most advanced in the world. The Eschede disaster forced engineers to reconsider important assumptions about maintenance and wheel design. In response to the accident, Deutsche Bahn launched major technical changes throughout its high-speed fleet. Trains using similar wheel systems were inspected and modified. Maintenance procedures became more strict, inspection intervals were shortened, and additional safety checks were introduced across the network. One of the most important changes involved ultrasonic testing technology. These inspections allowed engineers to detect hidden cracks inside wheel components before visible damage appeared. The new procedures dramatically improved the ability to identify fatigue problems long before they could become dangerous. The disaster also influenced railway safety standards beyond Germany. Engineers and transportation authorities in other countries reviewed their own wheel systems, inspection methods, and high-speed rail procedures. Lessons learned from Eschede contributed to broader improvements in railway safety throughout Europe and other parts of the world. For many Germans, however, the memory of the disaster was deeply personal. Families lost loved ones. Survivors carried emotional scars long after the physical injuries healed. Rescue workers and investigators also described the event as one of the most difficult moments of their professional lives. Memorials were later established near the accident site to honor those who lost their lives. Each year, people continued to remember the victims and the events of that summer morning in 1998. The location became a symbol not only of tragedy, but also of the importance of engineering responsibility and safety. The ICE network eventually recovered and continued expanding across Germany and Europe. Modern high-speed trains became safer, quieter, and more technologically advanced than ever before. Yet the Eschede disaster remained an important reminder that even highly sophisticated transportation systems can still be vulnerable to small, unnoticed failures, In many major accidents, investigators search for a single dramatic mistake. But the Eshede disaster was different. It was not caused by sabotage or reckless behavior. Instead, it emerged from a combination of engineering weaknesses, hidden material, fatigue, timing, and the unforgiving physics of high-speed travel. What made the event especially shocking was the reputation of the ICE system itself. Passengers believed they were traveling on one of the safest rail networks in the world. The train looked modern. The ride felt smooth. Nothing inside the cabins suggested that a dangerous mechanical failure was already unfolding beneath the floor. The disaster permanently changed how railway engineers approached wheel inspections and component fatigue analysis. It also demonstrated the importance of designing systems capable of detecting failures before they escalate into larger emergencies. In transportation engineering, small defects can sometimes create enormous consequences. Today, high-speed rail remains one of the safest forms of transportation in the world. Millions of passengers continue traveling safely every year aboard trains inspired by systems like the ICE. Many of the protections now considered standard were strengthened or introduced after lessons learned from the Eshede investigation. More than 2 decades later, the disaster still stands as a powerful case study in engineering, safety management, and emergency response. Universities, transportation experts, and railway investigators continue examining the accident to better understand how complex systems fail and how future tragedies can be prevented. What began as a normal summer journey between Munich and Hamburg lasted only a few minutes before becoming one of the defining railway disasters of the modern era. The Eshede accident changed high-speed rail forever, not because people stopped trusting trains, but because the tragedy forced an entire industry to become safer than it had ever been before.